Hello students, welcome to EduRev. Have you ever wondered how a tiny vibration becomes the sounds we hear all around us? In the next few minutes, we'll gently explore how sound is produced, how it travels, and why it feels so familiar to us. We'll meet the vibrating source, the medium that carries the disturbance, and the waves that carry energy from one place to another. Sound begins with vibration, a simple to and fro motion of an object that nudges the air or solid or liquid around it. Pluck a rubber band, strike a metal bar, or blow across a flute, and you create vibrations that push neighboring particles in a regular pattern. Our vocal cords work the same way inside the throat, and many animals use rubbing or striking body parts to make sound as well. A tuning fork makes this idea easy to see. Strike it and bring it near your ear. Put its prong in water and you can watch waves form as it vibrates. Those little waves show us two ideas at once. The source is moving and a disturbance spreads out from it in many directions. Sound cannot travel on its own. It needs a medium, solid, liquid, or gas, to carry the disturbance. Experiments such as placing your ear on a desk or tapping metal spoons underwater show sound through solids and liquids, while a bell in a vacuum jar becomes silent as the air is removed. That vacuum experiment is a clear reminder. Where there is no medium, sound cannot reach us. To picture how sound moves, imagine a slinky or a piston in a tube that pushes and pulls air in front of it. The piston's forward motion creates compressions, regions of higher density, and its backward motion produces rarefactions, regions of lower density. These compressions and rarefactions travel outward as a sound wave, even though the individual particles only vibrate back and forth about their positions. Because the particle motion is parallel to the wave's direction, sound is called a longitudinal wave. And since it needs matter to travel, it is a mechanical wave. A sound wave carries energy, but not matter. And that energy is what makes a thin sheet vibrate or grains jump in a demonstration. Two useful numbers describe waves: wavelength, the distance between successive compressions, and frequency, how many oscillations pass a point each second. The time for one oscillation is the period, and frequency and period are simple inverses of one another. Together, wavelength and frequency set the wave speed by a neat relation. Speed equals wavelength times frequency. V equals lambda times nu. Speed depends on the medium. Sound moves fastest in solids, slower in liquids, and slowest in gases. And temperature or humidity can change it too. For example, sound in air is about 331 meters per second at 0 degrees Celsius and roughly 344 meters per second around room temperature. That difference is why lightning is seen before thunder is heard. Light travels so fast we see it almost instantly, while sound takes time to cover the distance. Human hearing typically spans 20 Hz to 20 kHz, which corresponds to very long waves of many meters, down to centimeter-sized waves in air. We sense frequency as pitch. Higher frequency sounds are shrill and high-pitched. Lower frequencies are deep and low-pitched. Amplitude controls how energetic the wave is and how loud it sounds. Larger amplitude means more energy and a louder sound, measured in decibels. Loudness is subjective, but intensity is a measurable quantity. Sound energy crossing a unit area per unit time, and it falls as the wave spreads out. Reflection of sound gives us echoes. When a strong reflection arrives, at least a tenth of a second after the original sound, which translates to a rough minimum distance of 17 meters for a clear echo. In large halls, many quick reflections cause reverberation, which designers control with materials and shapes to keep speech clear and music warm. Our ears are elegant receivers. Sound vibrates the eardrum, tiny bones amplify that motion, and the cochlea turns it into electrical signals the brain understands. Having two ears also helps the brain locate sounds by tiny differences in arrival time and intensity between the two sides. Not all sound is meant for our ears. Infrasound below 20 Hz helps us study earthquakes and storms, while ultrasound above 20 kHz is invaluable in medicine and industry. Bats and dolphins use ultrasonic echoes to navigate and hunt, and humans copy that idea with sonar to detect objects underwater. Musical quality comes from more than pitch and loudness. Timbre, the mix of fundamental and overtone frequencies, gives each instrument its unique voice. A pure tone like a tuning fork has a single frequency, while musical notes are rich combinations of frequencies that create pleasant sounds, and octaves where the frequency doubles. There are practical tools built on these ideas. Microphones convert sound vibrations into electrical signals, and speakers reverse the process, turning electrical signals back into vibrating air. Everyday problems, such as noise pollution, remind us that prolonged exposure to loud sound can harm hearing. So, understanding intensity and protection is important. Before we finish, here is a useful quick calculation you might try. If thunder arrives 5 seconds after lightning, multiply the speed of sound by 5 to estimate how far away the storm is. That simple trick connects a concept to the real world and makes the physics feel alive. The key insight to carry with you is gentle. Sound is energy carried by organized pressure changes in a medium, not by particles traveling from source to ear. Knowing this helps explain why sound behaves differently in air, water, and solids, and why engineers and biologists use sound so cleverly in tools, medicine, and nature. Quick recap. Sound comes from vibrations, needs a medium, travels as longitudinal waves made of compressions and rarefactions, and carries energy measured by amplitude and intensity. We also saw that frequency and wavelength set the speed relationship. Echoes and reverberation come from reflection, and ultrasound and infrasound have powerful applications. Thank you for joining this gentle tour of sound and waves. I hope the ideas feel clearer and a little more magical now. If this made you curious, keep experimenting safely with simple demos like a tuning fork, a stretched string, or listening for echoes in a quiet corridor. Softly now. Goodbye for the moment. And remember, learning is a steady vibration. Small pushes add up over time. To learn more, visit EduRev for detailed notes, interactive quizzes, and videos that will help you practice and master these ideas. Stay curious, take care of your ears, and I look forward to exploring the next topic with you on EduRev.